Okay, so hello everyone. I'm Juancito. I'm a smart contract engineer, a blockchain security engineer, and a lot of other things. But I'm currently working on auditing and performing security reviews. I'm also participating in contests like Code Arena and Sherlock, and today I'm especially celebrating because I got the second place in the Lens Protocol
What?
V2 contest in Code Arena.
That's
Just
why Pepe
below
is here?
Milo Track, who's sorry.
That's why Pepe is
That
here?
happened yesterday, so yeah. And yeah, I was saying just below Milo Track. I think Milo is talking in a few days here in Open Sense as well. So we are both celebrating. So that's enough about me. Let's jump into today's talk, and it's about a repository I created called Multi-Chain Auditor. It's a compilation of observations and tips for auditing protocols on multiple chains. So if you are deploying on Ethereum and Polygon or Base and Optimism, there are some slight differences between them. And you may want to check this repository to know of any possible vulnerability or issues that you may experience. Also, if you are auditing on some competition, you might check it as well. It's open for contributions of any kind. And also, I put a disclaimer, please don't spam audit contests with these observations just because you see them here. Please do your own research and check any vulnerability and impact that may have. So that said, let's jump into the observations. There are quite some. I'll try to go not very deeply into all of them, but just go through all of them for you to have an idea of what's going on. So let's start with the first one. So first thing I want to talk about is about block time and block production on different chains. So as you probably know, the average block time in Ethereum, whenever a block is not mined but verified now, is around 12 seconds. We can see that on their on Etherscan, for example, the average block time nowadays is 12 seconds after the merge, which happened on this little spike. But it changed, like some years ago it was 13 seconds, some more years ago it was 16 seconds, 17 seconds. So as you see, the block time is different over the years, but it's also different on different chains. For example, in Polygon, you can see the average block time is around 2 seconds, different than the one that we check on Ethereum.
One question here.
So if you are using...
One question for you here.
Yeah.
After EIP 1559, block time got really consistent, right?
Yeah. So nowadays it's more consistent, and I think it should stay consistent over time. But the thing is that for some reason, some security reason, the Ethereum chain, they decide that it's not safe enough to have a time of around 12 seconds, and they decide to move it up or down. So that might change in the future. So it's true that nowadays it's more consistent, and we should not experience this kind of spikes. But in the long run, so in some years, it might be a different number than these 12 seconds.
Awesome.
But the observation is quite accurate. So this is an average. So if we go day by day or like block by block, we may experience that it's 12 seconds, but we see that it's 12:15, 12:14. So it might slightly vary. In mind. And another thing about Blocknumber that you should take into account is not the same for every chain. So in Ethereum, you know the block number is the block number of Ethereum. That's fine. In some layer 2s, it should behave as you expect. For example, in optimism, the block number is the block number of optimism. But on Arbitrum, for example, it's different. And the block number does not reflect the block number in Arbitrum. It reflects the block number in Ethereum. So that's kind of weird. So if you check the block number as you usually do when you're performing some auction duration or something that's time related, you might find that the value is slightly different because it does not reflect the actual Arbitrum block number, but the Ethereum one. And it also behaves in a weird way because, as you can see in this table, the L1, so the Ethereum block number, is not updated like every block. That's also some other difference. It's updated once per minute, I saw on the documentation. So let's say that you have an Ethereum block number 1000, 1001, 2, and 3, and 4, and you check the block number on Arbitrum, and it will say that at 12 a.m. it's 1000. You check again when the Ethereum block change, it's still the same number. You check it again some seconds later, it will still be the same. And after 1 minute, it will be updated, and it will not be a discrete change from 0 to 1 or from 3 to 4, but it will change a block number from 1000 to 1004. And this specific change might lead to other type of vulnerabilities. I think I have some reference here. Will not go into the specifics if it even loads. But the point is that someone can try to, let's say, make some staking on this specific block and perform some unstake on the very next one. And the protocol may expect that this will be a discrete change, so from 0 to 1, but you actually waited for 4 blocks. So
Can we talk a little
you
bit
may have
about
some calculations like they had on this specific issue on the Tigris contest
Can we talk a little bit about
that
that?
they are
you know?
using
So about
block number
how
for timestamps, and they experience this not discrete change where it happens what I said before, that they change from 0 to 4. So calculations are wrong, and like some other side effects may happen. So what you should remember about this is, in order to prevent all of these kind of issues, you should check that the block number preferably is not used as a time reference, and try to use, in this case, like block.timestamp might be a better option. So again,
nice.
like check if this is severity, if it impacts on the protocol, but just have this in mind when you are checking block numbers in these kind of chains. So that's about the block time. Let's jump into some other topic. This is a fan favorite of people who are auditing on contests because a lot of projects miss this one. If you're auditing, you might have seen the Chainlink fees and the Chainlink uptime, and not to get stale results. But specifically on layer 2s, you have to check for another specific check, which is that the sequencer is up. You know that in layer 2s, there are usually sequencers that like put all the transactions. And if they are not up, the transactions may not happen. And if that doesn't happen in Chainlink, the price fees may get old and you may have all results. And if you are a lending protocol or a DeFi protocol, you might want to have like results of prices like very precise and they don't get stale. So Chainlink has some recommendations in their documentation. So if you are using Arbitrum or using Optimism, Base, or Metis, they have specific checks that you want to use while you are checking prices in Chainlink. There was some example here that I got from one finding in one protocol. You might want to check if the sequencer of the specific chain that's using Chainlink is active. If it isn't, it might lead to different results. So, for example, we have here that the Arbitrum sequencer is down, and it can impact for malicious actor to gain an unfair advantage on some taking or some liquidations. So it can impact in many ways, but what you should check is that the sequencer is active. And if you go to the documentation on Chainlink, it specifies how you do that. It's basically checking that the sequencer has it's up, and the timestamp it provides is between the grace period you are expecting. So we'll talk about some other things with Chainlink later, but this is an important one that you should check, and I have seen that it has been rewarding on many protocols. I also see that Pashov on Twitter talk about this and be mindful about when you're using this, because there might be some edge cases that this is not valid. So please go through these issues and try to understand what's going on under the hood before posting some finding. So here's another Chainlink issue that you might also check, and it's also about the price feeds. And let's say that you are using a price feed in Ethereum, and you might also want to deploy on Base or Polygon. So you say, okay, I'll just add the chain, add the price feed, and that's it. But you might find that on Chainlink, not all price feeds are on all chains. So for example, on Ethereum, you have a large base of contracts. So all of these contracts, and you have like 172 entries to check price of Atom versus ETH or VAR versus USD, and a lot of others. But if you go to some newer chain like Base, for example, you might find that some of the feeds that you may find on Ethereum, like probably Link USD, they have it everywhere. But LTC USD, you might not find it in Base. So that's something that you should also check. Check that all of the feeds you're using on Chainlink are available on that specific chain, or you may run into some issues. You're trying to lend some money on some protocol, and you will find that there's no feed, so the function will probably revert, and you might experience some issues there as well. So you might not want to deploy all your features in all the protocols, or you may want to find another price feed provider that might not be Chainlink. So you might want to check that out as well. And now that I mentioned Chainlink, I might also mention integrations with other contracts. So with any contract that you interact with, please check that you are using the correct version on Ethereum, the correct version on other chains, but also check that they are available on all of these chains. We saw that on Chainlink, and we might see it on Uniswap, for example, or another AMM, that you might have some pair that's available on Binance Smart Chain, but it's not available on Optimism, or they might have different addresses. but specifically talking about AMMs and Uniswap, I like to mention one specific issue that you might find here. And as you know, in Uniswap, you have a token 0 and a token 1, which represents each token in the pair. And you might expect that they are the same on every chain because you have a pair that's web versus USD. But you might find it funny and interesting that this doesn't happen on all chains. The reason is that the token 0, token 1 order are derived from the addresses. So if if token 0 address is less, I think, than token 1, it goes first. And if token 1 is bigger than token 0 address, it goes after that. And you might find this difference when you check the pairs. So I open here the wrap Ether versus USDC pair on Arbitrum versus on Polygon. And we can see that the token 0 on Arbitrum is this address. So it's the wrap Ether. But if we check the same token 0 for the same pair on Polygon, we might find that it's actually USDC. If we check the token 1, we'll see it's the wrap Ether. So they are reverted. And what does this mean for us? Well, if you check the price, you'll see that the price is the relation between token 0 and token 1. So it's how many wrap Ether are per USDC or how many USDC are per wrap Ether. So the order is very important. And if you go to check the price here in slot 0, you check the latest price, but don't use it as a reference. Use an oracle for this, but we can check the price here. And we see the price is this huge number. And if we go to Arbitrum, we can check the same price and it will be completely different. And we can see it also has a lot of decimals in differences. And this is because of the reason we said it's doing how many wrap Ether are per USDC, and the other one is doing how many USDC per wrap Ether. So the advice here is, of course, verify the token orders. So you may check it everywhere, but especially if you're using multiple chains and you check that the addresses are the specific ones, we see that these addresses are different, but don't expect the tokens to be the same. So that's the advice on this one. Now let's move on to another kind of subtopic. It's about opcodes. We mentioned some with the Blocknumber, but Blocknumber is not the only opcode that's different on different chains. Each chain might have a lot of different opcodes, or they might have more opcodes, they might have less opcodes than on Ethereum, and they might have the same opcodes that behave differently. So, for example, in Optimism and in other chains, you can check the differences. This is from the previous version of Optimism, not Bedrock, but for the case, it's the same. And you can see some differences with Ethereum. For example, the Coinbase on Ethereum, it returns the Coinbase where the block was mined or validated or added. And in Optimism, it's undefined. You might not use this one, but you might use the block difficulty to create pseudo randomness on Ethereum. Not randomness, use an oracle for that. But in Ethereum, it might be more random or more reliable random as on a layer 2. And then we have other examples like the Blocknumber that we mentioned that's different on, might be different on L2, or the transaction origin and color that I think we'll talk about that later. Specific mention to push 0. This is an opcode that was introduced on Solidity version 0.8.20. You might have heard of that because of some issues on some chains that were afraid that this opcode was added to Solidity, but it was not implemented on all chains. For example, on Optimism, it was not supported. I think it might be supported now in Bedrock, but we can see that in Arbitrum, for example, this specific opcode, they still have that it is not yet supported. So if someone knows if I'm wrong here and they didn't update the docs, let me know. But what you should take into account into this is that you might want to pay attention to Solidity versions. So for example, if you're using a layer 2, you might want to check that this specific push 0 opcode is available on that chain, because maybe you're not using it, you're not doing some assembly and using this push 0, but the compiler might use it under the hood and it might introduce some issues, some unexpected errors. So for now, the safe advice is for layer 2s that do not implement it, use a previous version. Or I saw in Twitter there was some option that you can configure when you compile the contracts that you can use to safely use a later version. Don't remember it at the moment, but have this in mind when you are deploying a contract or checking some contract on some layer 2. Also check, as we mentioned, differences with Ethereum on different chains. So if you use block difficulty, block base fee, transaction origin, so different opcodes that they behave the way you expect on the different chains. In most cases, they will, but there might be some slight differences. So another thing you like to check when you are doing some reviews. And we mentioned transaction origin and message sender. So this specific example, this codes behave the same in Optimism, let's say, if you're interacting with the same contract. So it will be exactly the same as on Ethereum. There's no link here, sorry. So it might behave exactly the same, but it will be different if you're interacting between a layer 1 and a layer 2. If you send a message from a layer 1 to a layer 2, it might be slightly different. I cannot find it. I might update these checks. But what's important here is that when you are using transaction origin, that you might not want to use it, but if you have some good reason to use it, and you are doing some cross-chain interaction, this specific value will be the value of the layer 1 chain plus some specific bytecode. So it will not be the message sender always. So that's something that you should check. But the advice is the same as before. Verify that the behavior is the same for the specific opcodes on the chain that you were developing your project or auditing in Ethereum, for example. Verify that these opcodes behave the same way, and if they behave differently, try to check if that applies to your project. In this case, it probably will be safe, it will be the same. But if you're doing some working on some project that does cross-chain messaging, that might be some issue. As I mentioned, cross-chain message vulnerabilities. Let's jump into one. So, as you know, some protocols do cross-chain messaging, and cross-chain messaging might introduce new issues. So there's no specific rule for this, but I can give you some example. Give you 2 examples here on 2 different protocols, on pull together and in Derby. And in pull together, there's a function in L1 that calls Arbitrum. called process calls that calls this create retry all ticket. So there's this function, a person A relays a call, so to executing on Arbitrum, and then a user B can process this call. So we as the user, we try to relay a call, and then as it is usual on many protocols, anyone can process the calls. So it should be not an issue. The thing that happened on this specific case was that anyone can relay a call, anyone can process a call from any other person. But there was a bug here that when they create this returnable ticket, that this is the message that will be executed on Arbitrum, they are using this specific value called call value refund address, which is the one that specifically on the documentation says, be careful, since this address can cancel the retry all in the layer 2. So what does it mean? It means that I, as a user, can relay a call. Anyone can process it, but when they process it, they might end being the person who can cancel the same call. So an attacker can grief the protocol and process all of the calls from everyone, and they might be able to cancel them. That's because when they are relaying this message, they are creating this retrievable ticket. This specific value, which is the 1, 2, 3, 4, 5, it's here. So 1, 2, 3, 4, 5 is the message sender. So whoever calls these process calls will be the person who will be able to cancel the ticket. So that's very specific to this protocol, but you may want to pay special attention to authorization. And when you're doing these cross-messaging applications, that you might not give the person who executes these messages, who executes with retrievable tickets, to have more permission than they have. So in the other example that I had on another issue on the Derby protocol, it's a very similar issue. So it's an issue with cross-chain message authentication that can be bypassed. So we can see that this can be an issue. So in this case, in the previous one, it allowed a user to cancel transactions, an attacker. In this case, it allows an attacker to disrupt the state of the vaults. So this can lead to a high vulnerability issue. So in all of these cases, when doing cross-chain messaging, please be very mindful on who's the one that's relaying the calls, who's the one that's processing the calls, and what permissions do they have when they do that. So that's the main advice on these cross-chain message vulnerabilities. You may find a lot of others because
Very interesting, bro.
each protocol will have different, but the general message is be very mindful on authorization because it seems to happen quite a lot on this.
Very
That said,
interesting.
another subtopic is about gas, let's say.
Awesome.
And in this specific issue, I'll talk about transfer and send. So these operations are operations that might not be very used or encouraged to use, but you may find this on some repositories, on some protocols. And as you know, transfer and send are used to send some Ether or the native token on each chain. And the specific feature bug they have is that they forward a hard-coded amount of gas. I think it's around 2300 of gas. And if you have a callback, so you can transfer Ether to a contract, and that contract can have a receive function or a follow-up function, you can execute some code. But that's limited to a specific amount of gas because of how these operations work. This is kind of discouraged for many things, but in the case of multi-chain, it's discouraged because gas costs can change and they might be different on different chains. So you might find that this transfer and send function use a specific amount of gas on Ethereum, but on some other chain they might use some different value. And if you're expecting to execute some functions on the fallback or on the receive, they might be able to be executed on some chain, but not on other. And in the specific case of zkSync era, some months ago, on April, there was this project that ran into a problem. The problem was that they were using transfer and send. And as I was saying, this function forward a hardcoded amount of 2300,000 of gas. But the fallback was calling some other functions, and these specific functions meant that they couldn't run, and it was kind of like a denial of service error they had, and funds from many users were locked in the protocol. I think they fixed it somehow, but the general advice here is that look into some of these fixed gas operations. They might behave differently. They might have different values on different chains, and they might also change over time. So in case you don't want to run in some issues that happen on that project, please be mindful on that. And also talking about gas fees, we know that gas fees in Ethereum are quite expensive. On some other chains, they might be cheaper. And as they might be cheaper, that means that you may perform some attacks on those chains that you might not be able to do on Ethereum because it's not monetary possible, because you'll spend a lot of money. But some people might perform even a griefing attack, so a kind of attack that doesn't make any profit for the attacker, but harms users or the protocol. And that can be of many forms. So on some chain that's really cheap, you can perform some attacks to deny of service some function because of unboundarize or boundarize. That means that you can push elements into some array, like kind of indefinitely, and at some point the array size won't fit into memory, and that will make the function revert always. So that is unfeasible on Ethereum, but on some very cheap chain, you might be able to call a function all over and over and over again, and you might be able to perform such an attack. Same thing with spamming. You can spam some function a lot of times. You can spam the events, so you can have a lot of events to mess up the protocol events and processing they have, or even some specific function on the contract. So you can also check, this is more interesting. You may find that you found a vulnerability and it drains a very small amount of Wei or tokens. And if you perform that attack on Ethereum, you might be paying like $5 per function execution. So in order to steal some Weis, it won't be profitable. But you may use Polygon or even a cheaper chain that this attack may be viable, because some ways of USDC that has 6 decimals might be some cents, and the cost in Polygon to execute the transaction will be also of some cents or less. So that might be viable here. also front running. So in Ethereum, you can front run an operation, but in order to front run an operation, you have to pay more gas than the person who executes it originally. So you'll end up paying a lot more for an attacker if they want to do so. But on some cheaper chain, this might be like cheaper. So there's a specific example also from a Griffin attack that I can show you. So the issue here is that an attacker can force Surge to never, so Surge is the name of the project. An attacker can force Surge to never update the collateralization ratio. So this is very specific to the protocol, but what we want to take notice on this is that they have some function. It doesn't matter. It's some function to update the collateral ratio. And some attacker can front run it because they might have some open permissions or so. And they might prevent the protocol from changing it, or they might prevent some user from executing some function because of some mischeck on the protocol. You might do it once, you might do it twice, but in the end, the user can try to execute it as many times as they want, and they might finally be able to execute the functions. What's important about cheaper chains is that you might have a bot or some automated function that might perform the attack over and over and over again, and you might prevent some user from being liquidated, let's say. And if you prevent some user from being liquidated over time, over 1 hour, over 2 hours, over 1 day, you might find that the impact might be higher than if you just prevent it one time. And this is possible only if it is economically viable. And if every time you try to front run an operation to prevent, let's say, some liquidation or unstaking or some other function that impacts the user, might be very expensive to do it on Ethereum like 100 times. But on Gnosis chain, for example, it might cost you some cents or $1 to do it 100 times. And with a sustained attack, like over minutes, hours, or even days, you might find that it's still viable economically. So that's another thing you might want to be mindful. Like gas fees, lower gas fees enable this kind of attacks that might not be possible. Or they might be possible, but they might be very expensive to execute on Ethereum. And now that we talk about front running, I think you'll know what front running is. We mentioned it is when some transaction is executed. So when an attacker or someone wants to spend more gas to execute their transaction first before some user. So this is possible on many chains. And some example was the previous vulnerability that we mentioned. But you might find it interesting that it's not possible, or it is very difficult, as they say. In Optimism, for example, they say, is transaction from running possible on OP mainnet? This is the previous version of Optimism. But their answer is that front running is difficult. Why is that? It's because Optimism and many layer 2s have a private mempool. So the mempool in Ethereum, for example, it's public. So every transaction that's queued to be executed goes to the mempool, and whoever puts more gas to execute it, the validators, the miners, or depends on the chain, the people who are creating the blocks will choose a transaction that gives them more gas or more money. And in Ethereum, this mempool can be seen by everyone, and you can see transactions that are still not executed, and you might be able to front run them to get some advantage, maybe. But on the case of Optimism, Arbitrum, and some other chains, they have a private mempool. So most users are not able to see what people are executing because usually they have some sequencer that executes its transaction like sequentially. So the first transaction that enters, the first that is executed, and attackers cannot see it. It's kind of the same things that happens with flashbots, that you are not able to see what's going on under the hood. So that might prevent some kind of these front-running attacks. So it is also worth mentioning this because you might be doing some auditing, for example, and you might find some front-running possibility, which is viable on Ethereum. But if the protocol is just only using Optimism, it might be very difficult or impossible to do this kind of front-running or sandwich attacks. So pay attention to that and be mindful when you're submitting this kind of vulnerabilities. So let's jump to another topic. There are not many, so let's jump to the last 4 or 5. And this one is quite important. You might note about signature replay attacks. Signature replay attacks are when one specific signature that you might use to authorize another person to use your tokens, stake them, deposit them, or liquidate someone, or many other actions. You give your specific account signature to allow them to do different actions. The thing is that you allow some people to do different actions, but only once. So you may allow a protocol to spend your USDC or USDT tokens just once, but you don't want them to spend them all over and over again. So they might check that, and they might introduce nonce so that you cannot execute it the same signature many times. But you may find interesting that you might have the same nonce, you might have the same transaction details and the same signature. And if the protocol is deployed on different chains, they might be able to reuse this specific signature on different chains. For example, let's say that Uniswap deploys their token pair, anyone, BTC versus ETH, or wrap BTC versus ETH. And they do it on Ethereum and they do it on Polygon. And I approve someone to use the tokens to swap or to perform some specific action. On Ethereum, they might be able to do it. But if the protocol is missing some check that we'll see, they might be able to do that on other chain as well. So that means that I might be able to approve some tokens to be used on Ethereum, but if I happen to have those tokens on other chains, they might reuse this signature and steal my tokens or use them for other means. So in order to prevent these kind of issues, it's important that if you're deploying your project on multiple chains, that you check the chain ID and you add that to the domain separator or to the digest that you're using for the recovery function, that in this case for the permit, but on any different function that you are using a signature. So in other words, if you are signing some message and you are recovering the address, please check that you are adding the chain ID, because if you don't add the chain ID, you might be able to replay it on all of the other chains if the protocol is running on those chains. So check it and check all of the other things like nonce, values, and all the the common things that you might want to check when you're doing signatures. But on this specific case, please check that you add this domain separator with the chain ID. And you might also want to reevaluate this domain separator because some chain might fork and the chain ID will change. So you might want also to reevaluate this domain separator in case you want to be able to have in mind those kind of cases. Okay, so let's move to a simpler one. So this was kind of hard to explain because it had many components, but this one I hope it's easier to understand. We talk about this check of any hard-coded contract addresses that you might see on the contracts. You may see that because it's easier for writing and easier to debug and easier to deploy, you might find many contracts that have their addresses hard-coded, and that might be fine if the project is just deployed on one address. But if the project is successful, they might want to deploy it on other specific chains. And they might run into some issues like it happened on this specific contest. So this was not released, but it was on the Derby protocol contest on Sherlock. And the thing that happened here is that the protocol will not work just like that on many of the expected supported blockchains, just because they hard-coded the web contract address. And if you check the code, they have this line that they say the contract address of Rapidfair is this one. And this works for Ethereum, but the protocol was expecting to deploy the contracts on Arbitrum, Optimism, Polygon, Binance Smart Chain, and all of this as well. So you will find that specifically Rapidfair, I think that on all of these chains, they have a different address. So this seems like a kind of a silly mistake, but if you are working on multiple chains, you might want to check this. And instead of putting some constant value for it, maybe you can add it on the constructor or initialize function, and you can provide a specific address when you're deploying on each specific chain. So this doesn't happen only for Rapidfair, but if you are using some Chainlink feed, or if you're using some Uniswap pair or any protocol, you should check for each of these protocol of each of these chains that the addresses are correct and they are the ones that you are expecting. Because otherwise, probably best thing that could happen is that the protocol won't work, but you may run into some other issues like funds block. Maybe you're using this function on some unstake or some withdraw function, and you may find that users might be able to deposit but not withdraw, or some other more complicated issues. Similar to this is with ERC20. Something funny that maybe some of you won't know is that token decimals on different chains might be different. So in the case of USDT and USDC on Ethereum, most of us know that it has 6 decimals, but on some other chains, interestingly, they have different values. We can check that. On Binance Smart Chain, the token decimals is 18, and in Ethereum it's 6. And it's the same token, it's deployed by the same people, but they have different values. And you might expect that this can have a lot of really critical issues if you just want to work with this specific token and you expect that it has 6 decimals and you find 18, you might have into not precision loss, but very bad accounting issues with this. So have that in mind. And also talking about funny tokens, you might find that the contract interfaces for the same tokens or the same kind of contracts might behave differently. Another example, USDT. I think that if you check the USDT contract on every chain, you might find all of the things we've been talking about over and over again. So to put it simply, on USDT, the interface is very similar to what we expect, but it doesn't return any value. And on other chains, like Polygon, for example, it behaves as it's expected from the ERC20 specification, the EIP 20 specification, that it should return a bool value. So this might not seem to be very important, but if you're using some interface like interface ERC20, you might interface it like this. And if the token doesn't return a value, the function will revert. So if you don't take this into account, you might expect this token to return a Boolean. You might want to check it or so, but you will find that this function will revert if you are not mindful about that. So you can use safe transfer, or you can, if you are sure that you are using USDT on Ethereum, you can just use this interface. But check this, that the contracts that you are using all respect the same interface. So again, the advice is the same like previously. Please check each contract that you are interacting with on all of the chains. Same with contract upgradability. We saw here that the USDT is deployed on Ethereum like an immutable contract, but on Polygon it's using a proxy. So they might also change this implementation. They probably won't, but they might add some functionality, which won't be possible on Ethereum, for example. And last thing about contracts, and almost last thing about this talk, is that contracts may behave differently. So you might have the same interface. You might have the same upgradeability, or they might be immutable, but contracts may behave differently. So they might call this transfer function, and they might do things slightly different. So for example, on XDAI chain, that was the previous Gnosis chain, the tokens for USDC, wrapped Bitcoin, wrapped Ether, and many others contain a post-transfer callback. So this is the same as with the NFTs, and you use safe transfer with NFTs, that whenever you transfer a token, there's a callback that's executed, and it can lead to reentrancy bugs. It also happens with a specific ERC777 tokens that they have a callback. But if you check on any chain, USDC, wrapped Bitcoin, wrapped Ether, they don't have a callback. And let's say that your manager wants to deploy the project on Ethereum, but they wanted to deploy it on XDAI and 100 different chains because it's the same. Well, it's not really the same. In this specific case, XDAI had this post-transfer callback. It deriving some exploits, and they had to hard fork the chain, which they ran into many issues. They rebranded as Gnosis chain and so on. But this is a very specific case, but the advice is similar to the previous one. For each contract, do not only check the interfaces, but check the implementations that they behave the same. It might take some time, but you might find some funny and interesting issues that you will not expect to happen. And that's almost it, because the last 2 points are just mentions. So some chains have some precompiles. These are specific contracts that are deployed directly on the chain. So for example, Optimism has the Rapid for token deployed to them. And I wanted to mention that because it has a funny address, but it doesn't load. It starts with 420. That's it. But they have different precompiles and different
Nice.
contracts that if you're using them, they might be slightly different on each chain, and they might have a slightly difference on their addresses. And the last thing is about zkSync era. I put that as a specific case because, as previously mentioned, there are a lot of EVM instructions and opcodes that
Awesome.
may be different on different chains, but on this specific one, they differ a lot, or at least there are quite a lot of examples. You might want to check them if you are working on this specific chain, or if you are auditing it. So go over it, and you might find some interesting issues as well if you are checking some protocol there. Okay, so final note. Most of the chains have their differences with Ethereum. So you might want to check those links to see how different opcodes behave, how the timestamp, the block times differ from each one. You might find very interesting things for each different chain. So that's it. As I said, this project is open for contributions. If you want to check it, there are some other tools that you can check also here to see differences with Ethereum and Optimism in a table format. It was developed by MDS1 at MDS1, so kudos to him. And again, I hope you found
Bro,
this
really
talk
interesting, man.
and
Really
you
interesting.
find something that you didn't know.
Can you hear
And
me?
if you like it, please, you can start the repo. And you are encouraged to contribute it in any ways